Okay, so in this chapter we'll talk about linear momentum and collisions. Okay. So again, anytime, so we are introducing a new quantity, linear momentum, and anytime you introduce a new quantity, it's useful in certain circumstances. Okay, and that's why you introduce this. Okay. So our goal will be to deal with the following. Okay, so we have dealt with forces that change with position. Okay, and you saw that this quantity had a physical meaning. What was that equal to? Work done. And what did work do? It changed the energy of the system. If you did work, it changed the energy of the system. Okay? Now here, what we want to learn is how to handle situations like this. Forces that change with time. Okay? So let me give you a situation. Let me show you an example. Okay. So here's an example. Okay. So here's the bat exerting a force on the ball. Okay. And when the ball is coming here, what is the force the bat exerts on the ball? 0. So the force exerted is only during contact time. Okay. And the force, if you plotted the force as a function of time, this is before the ball is in contact. As it comes in contact, this is how the force looks like. Okay. This force on the ball lasts about maybe 50 to 100 milliseconds. And the peak force could be about 2,000 to 3,000 times the weight of the ball. Okay. So here's a rapidly changing force, and the forces can get large. And so to deal with situations like this, we'll define something called momentum, linear momentum. Okay. Now here's another thing that's going on. Okay. So in a situation like this, so this doesn't look very complicated, but this ball was moving up and down, it was slowing down and all that. So in physics, as a system evolves, we would like to say, does something remain constant through the entire motion? Okay. In this motion, are you aware of anything that remained constant? Mechanical energy. That's what you solve problems. Okay. Mechanical energy remained constant. Okay. All right. So I'm going to show you. Okay. So here's a pool table. Okay. And what we'll do is, so now this clip will last less than 30 seconds. So I'll explain what's going on. So what you'll do is you'll shoot a cue ball. The cue ball will have a momentum. Momentum will be mass times velocity. Okay? And when the cue ball hits this rack, all these balls will fly apart. And amazingly, the total momentum of the system will be constant. Okay? And so that's a very complicated looking thing, and we are able to say that the total momentum is constant. That's a powerful statement. Okay? You can throw a hand grenade and it breaks up into 1,000,000 pieces. The total momentum of all those pieces together is equal to the initial momentum. Okay. How long will the momentum be constant? Till a force acts on the system, till the first ball hits the side. Okay. Okay. So when it hits the side of a table, then a force is acting on the system, and now that'll change the momentum. Okay. So we can make statements like that, and that's what we're interested in. Okay, so I'll play this for a second, or maybe not. Okay, we won't worry about that. You guys have seen a pool table. All right, so we'll define linear momentum. This will be related to, so we'll be interested in handling situations where the forces act for a very small time, and that's true in collisions, so that's why we are studying collisions. All right, so we'll define linear momentum, collisions and impulses, conservation of linear momentum. That's what I just told you about. You are breaking a pool rack, and the momentum of this system, okay, or the pool rack is like so. Here's the cue ball coming, and it breaks up into a million pieces, and the momentum of all this thing is equal to the momentum of this thing. Okay, the momentum is constant throughout that till one of the balls hits the side of a table. Okay. And then we'll study various kinds of collisions. Okay. So here's a pool ball going in this direction, there's a pool ball coming like that, and they collide, and this guy goes off like this, and this guy goes off like that. So you see there's the initial momentum of ball 1, here's the momentum of ball 2. The sum of these two vectors is that, and there's the initial, this is after the collision, there's the momentum of ball 1, momentum of ball 2, and see their sum is the same. The momentum, final momentum, is equal to initial momentum. Okay. That's in pictures, and I'll show that to you in a simulation. Okay, so we'll do momentum vectors. So I'll show you a couple of things. So this is, we'll make it an elastic collision. We will not do a reflecting border. Okay, so these simulations go very fast. We'll do it slow. Okay, so, and center mass, momentum. Okay, so you can see that this will show you the total momentum as well. So there's the momentum of the first ball, there's the momentum of the second ball, and the total momentum after the collision should be the same. Okay, so I want you to watch a couple of things. First, we'll just watch the collision. First, we'll watch the collision, and then we'll watch this diagram, and you'll see that the total momentum remains constant. Okay. All right, yeah, so here's several collisions, and okay. Okay, actually that's messing things up. Don't want a reflecting border. Okay, so there'll be only one collision, and the total momentum will remain constant. Okay, so all right. Okay. Now here's another thing. Okay, so we'll talk about this. All right, so here is the center of mass of these two objects, and I'm going to get these objects to collide and watch what happens to the center of mass. Okay. All right, so look at its velocity before the collision and look at its velocity after the collision. Okay, so the center of mass moved with constant velocity. Okay. And we'll talk about that in a little bit as well. All right, so we will define linear momentum. We define another conserved quantity. What do we mean by a conserved quantity? A quantity that remains constant throughout the complicated motion of the system. Okay. Which will put an additional constraint on how systems evolve in time. Okay. So Conservation of momentum is useful for understanding collisions. Okay. Momentum is just as powerful, important, and useful as energy. Okay. The reason you don't hear more often about momentum at lower levels is because energy is a scalar. It's a simpler quantity. Momentum is a vector. You have to learn about momentum. Vectors. So it gets introduced later. Okay. Often we encounter situations where the applied force varies with time and is non-zero for extremely short intervals. Okay. So we want to handle situations like this, a force that lasts very short times. Okay. Like I said, in this collision, this is about 50 milliseconds. When you kick a soccer ball, that collision might last 150 to 200 milliseconds. So softer the ball, longer the collision time. Okay. So we'll define something called linear momentum. So there is linear momentum denoted by P. It's a vector quantity. It's mass times the velocity of the object. What is Newton's second law? Yeah. So force equals to mass times acceleration. Okay, so this is the special case. Okay, here is the correct form. Here is the more general form of Newton's second law. The force acting on an object is time rate of change of momentum of the object. Okay, and again, like I said, we talk about this because if somebody hasn't had calculus, and this is a special case, and we'll tell you what, this applies in most of the cases. Okay. So to do this, you of course have had to add calculus. Okay. So let's put in the d by dt. What is momentum? Mass times velocity. Okay, and from the chain rule, this is dm by dt times velocity plus m dv by dt. And this, of course, is acceleration, so that's mass times acceleration. So the net force. So when you see this equation, force equals to mass times acceleration, there is the force equal to mass times acceleration. Well, what happened to this fella? So they sold you a bill of goods when they gave you that equation. What happened to this fellow? All right, let's say you're driving your car. Is the mass of your car changing? I'm sorry?
Yes, it's burning gas, so it's changing.
Yeah, it's changing ever so small. So this term is very small in most of the situations. Okay. When you go running, is your mass changing?
Barely.
Barely. It's changing some. Okay, so in most of the situations, this is negligible. Can you think of a situation when you can't ignore this term? Rockets. So if you're Elon Musk, this is 90% of the term. In a rocket will lose 90% of its mass in a couple of minutes, in 3 minutes. Okay, so when you get to that situation, well, then by then you've had calculus anyway, so they'll tell you that equation. All right. So this is the more general form of Newton's second law. Okay. All right, so now that we know this, here's Newton's second law, dp by dt. Okay. This is change in momentum divided by the change in time over which that happened. That tells you the force that you need to apply. Okay. So here's momentum of various objects. Okay. An alpha particle is a helium nucleus. Okay, and so on. And here are the momentums in SI units. Now the reason they're listing this table is, so you can have a sense for what kind of forces are needed to stop this object. Okay, So if you want to change the momentum, you would want to stop this object. Look at this, a charging rhinoceros has the same momentum as that of a car. Okay, so you want to stop a rhinoceros and stopping a car are the same thing. Okay. A super tanker, see, its momentum is a billion times, well, greater than a fastball. Okay, so stopping a super tanker is not easy. You can stop this guy with a mitt in your hand. Okay. So if you can't apply a large force, then that means you would have to stop that object over a longer time. Okay. And boats, it's hard to, to apply a force on the boat, you have to reverse your engine. Super tankers take a half an hour to stop. Okay. So you got to plan for a stop and so on. Okay, again, large forces acting on you are bad for your health. Okay, so let's say if you're going at 80 miles an hour and you need to be stopped. Okay, if you don't want large forces acting on you, what is it that you do? You want to make this large. Your stopping time large, and that's what safety devices do. Okay, if there's no airbag, and if a steering wheel stops you, it'll stop you very fast and the force will be large on you. Whereas if you deploy an airbag, then you can make the stopping time large, make the force smaller on you. Okay, and in addition, what else does the airbag do? Okay, so here's another thing the airbag does. See, I'm applying a 15-pound force. Does that hurt? No. How about now? That hurts. Okay, so not only is it decreasing the force, it's applying the force over a larger area. Okay, so it's doing a couple of things. By the way, the airbags are a very good technology. What's nice about this? Do you guys know how this thing happens? Have you guys heard of the fact that they tell you not to drive it too close to the steering wheel? Why is that? They're telling you give the airbag enough time to expand. Okay, if you're too close to the airbag, this airbag expands at 200 miles an hour. Instead of saving you, it'll kill you. Okay, so that's why you don't want to be driving too close to the steering wheel. All right, so we're going to deal with a situation where the force that the club exerts on the ball lives for a small time, and so 50 milliseconds roughly, and can be quite large. Okay, so the magnitude of the force changes quite a bit. All right, now before we do that, you guys remember, so when you had a force that was a function of position, this area we gave a physical meaning to this area. You guys remember what that was? That was the work done. Okay, that was the work done. So we'll do the same thing for this area. Okay, and you'll see that this area, okay, is called the impulse. Okay. And that area is equal to change in momentum. Okay. What is the change in momentum? mass times final velocity minus mass times initial velocity. All right, so initial velocity was 0 in this case. Okay, so greater this area, faster the ball flies off. Okay, so greater the impulse imparted on the ball, greater the velocity of the ball. Okay, so now you guys know the difference between Tiger Woods and me. It's just a little area. Okay. Yep. Yep. All right, so again, here's force is dp by dt. Okay, so here's Newton's second law, and what we'll do is we'll integrate both sides with respect to time. Okay, so force dt. Okay, now I'll write this without vector symbols. Okay. And what is this equal to? That's equal to the area under this curve. Okay. And that is called an impulse. Some textbooks denote that by J, others denote it by I. So either J or I, that's the impulse, that's the area under this curve. And when you integrate this side with respect to t, okay, this is using the fundamental theorem of calculus, integration and derivative. So pt, t initial to t final. Okay, that's the momentum after the force has acted on you, and this is the momentum before the force acted on you. So that's the final momentum, that's the initial momentum. Okay. So this was the result of that force, of this force acting on you. Okay. This is called the impulse. Okay. That was the impulse imparted on you, and because of that, your momentum changed. Okay. This fellow acted on you, and so your momentum changed. Okay. All right, so this is the impulse momentum theorem, and this is, so when a force did work on you, when a force acts on you, it does work on you, and your kinetic energy changes, and also your momentum changes. Okay? The change in momentum is given by that quantity, the change in kinetic energy is given by that quantity. Okay, so we will do an experiment in lab where, so that'll be the best experiment we do. We'll measure this force acting on an object 500 times a second. Okay, so that's the most detailed measurement you'll do. Okay. Now, in situations like this, it's not practical to measure the force as a function of time. So what we are interested in is, well, what is the average force that was acting on it? Yeah. That's what we most often calculate, and the average force is defined as, okay, so it lives as long as the real force, okay, and the area in this rectangle is equal to this area. Okay, that's how we define the average force. So the impulse, this area is equal to the average force times the time over which the force lives. Okay, so now we'll make a statement of the conservation of linear momentum. Okay, so you just saw that Newton's second law was the net force acting on the object was equal to dp by dt, time rate of change of momentum of the object or the system. Okay, this applies to a system or to a particle. Okay, so the net force acting on the system was equal to rate of change of momentum of the system. Now it turns out that the forces can be internal forces. Okay, so when these guys collide, what happens? The balls compress, this guy exerts a force on this guy, and what does this guy do on him? So when two balls are in contact, This guy will exert a force on him. And what does this guy do on him? An equal and opposite force. Newton's third law tells us. Okay. So these internal forces add up to zero always. They'll always add up to zero, no matter what objects are interacting. Okay. So the net force is internal forces plus external forces. These guys always add up to zero. And so the net force acting on an object is any external force. What do we mean by external forces? If gravity is in play, though, that's an external force. You know? But when you're playing pool, is gravity playing any role? Gravity is there, but it's being canceled by the normal force, so it's not playing any role. Okay? So when you were playing pool, you shot the cue ball, and if there was no friction, external force was also zero. When the external force is zero, the momentum of the system does not change. And that's what we said. You hit the cue ball, you gave the system momentum, and now the momentum evolved, and as it was evolving, it remained constant. So, momentum remained constant. Initial momentum was equal to final momentum as long as external forces are zero. In the pool table, when you were breaking the rack, what was the initial point and what was the final point? Any point was initial point and any point was final point. The momentum was constant throughout. Till what? When was the momentum constant?
Until one of the balls hits the wall.
Till an external force acted. And as soon as one of the ball hits the side rail, an external force has come into play. All right. So this is momentum conservation. Okay, and so that's what happens in collisions when two cars collide. Okay, it's all internal forces, and so momentum before the collision is equal to momentum after the collision. Okay? It doesn't matter what kind of collision it is. Okay. And so they use this in labs all the time, in particle labs all the time. Okay, so here's a particle in accelerator. So here's a neutral kaon. So this is at rest, and this will decay into these two particles. Okay, this is a particle-antiparticle pair, and they have equal masses. Okay, so if this was at rest, what is its momentum before this decay? It's zero. And so this decay, you can think of it as an explosion. This thing has exploded into these two particles. There's no external force, so the momentum of this must also be zero. And since they're of equal mass, they are going at exactly the same speed, exactly in the opposite direction. So when this decays, this guy, if he's going at 10 meters per second, this guy's going at 10 meters per second. If he's going at 180 degrees, this guy's going at 0 degrees. Okay. So you know the parameters of this guy, you immediately know the parameters of the other guy. Yeah. In fireworks, the momentum of the shell just before it explodes is equal to the momentum of all the pieces right after it explodes. Okay? All right, so now let's look at types of collisions. So we'll be studying objects colliding. Okay. So what this says is if the final kinetic energy is equal to initial kinetic energy, that is the kinetic energy of the system after the collision is equal to the kinetic energy before the collision, then it's called an elastic collision. Okay? That's what happens in the pool table. Okay, so when these guys collide, the kinetic energy before is equal to kinetic energy afterwards. Okay, so this is so we are doing an elastic collision, and we'll show you the values of kinetic energy. Okay. Okay, so here is the kinetic energy, and this is before the collision, and you'll see that number won't change after the collision. Okay, so that's an elastic collision. Okay, so if the kinetic energy does not change, the collision is elastic. If you lose kinetic energy, well, then it's an inelastic collision. So if two putty balls collide, then you are losing kinetic energy, and that's an inelastic collision. And if the final kinetic energy is 0, then it's called a perfectly inelastic collision. So for instance, you can take two pizza dough balls and throw them at each other, and they'll stick and they'll stop. Okay? That's a perfectly inelastic collision. Now, if the final kinetic energy is greater than the initial kinetic energy, then the event is an explosion. See here, the final kinetic energy of all the pieces is greater than the initial kinetic energy. And so that's an explosion. So there, what happened, some kind of chemical energy or something was converted to kinetic energy. Okay. Okay, so here are two objects before they're colliding, and here they stick together, and after the collision, they've stuck together, and there's the final velocity. Okay, so now that we've learned, so if there's no external force acting on the system, so from the fact that the momentum before the collision should equal momentum after the collision, we can calculate they can only go at a specific velocity. Okay, so we are doing this in one dimension. Okay, so it doesn't matter what material the balls are made of or what their masses are. In 1D, if they stick together, the specific velocity they go with is the following. Okay, so there is the initial momentum. What that is the mass 1 times velocity of ball 1 initial momentum of ball 1 plus momentum of ball 2 is equal to, they've stuck together, their combined mass times the final velocity. And so here's the final velocity. The final velocity is the total momentum, initial momentum, divided by the total mass. Okay, so we are able to say this, so the final velocity is a very specific value. Okay. Okay, what is an elastic collision? Where no kinetic energy is lost. Okay, so for the special one-dimensional case, we can say something in addition. Okay, so here's two objects colliding, and they bounce off and go off like that. So here is the momentum conservation. There's the momentum before the collision, and there's the momentum after the collision. Here's the kinetic energy before the collision, and here's the kinetic energy after the collision. Okay, and you can do a little algebra, manipulate these two equations, and these two equations can be rewritten like that. Okay, this is the same as that equation. But then you also can write this equation. V1 initial final minus V2 initial final So this is the difference in the velocity of the two guys, equal to minus V1 final minus V2 final. Okay, what this means is the following. Let's say two balls are colliding. Okay. So this is going at 5 meters per second, and this is going at 7 meters per second. Okay. So this is 5 meters per second, and this is minus 7 meters per second because it's going in the opposite direction. So what is V1 final minus V2 final? 5 minus of minus 7, that's 12 meters per second. So what this is really is, if you were sitting on this ball, this guy is coming at you at 12 meters per second. That's what that number is. And then what this says is, okay, after collision, what happens? These guys bounce off like that. Okay. And now, see, initially it was coming at 12 meters per second, and if you're sitting here, you watch him and go away at 12 meters per second. That's what that means. Okay. Okay, so in one dimension, for elastic collision, you are able to say that. Okay. So if a cue ball hits this ball, okay, so if you're sitting on this ball, the cue ball is coming at you at 10 meters per second. In a pool table, what happens? This guy goes exactly at 12 meters per second, and this guy is at rest. So from watching from here, this guy is moving away from you at 12 meters per second. Okay, so we are going to say things for very special cases. Okay. So now we'll consider collisions in 2 dimensions. This is what happens in pool tables. Okay. So this guy collides with him. This is a glancing collision, and he goes off in this direction, and this guy goes off in this direction. Okay. So now momentum are 2-dimensional vectors. So initial momentum was only in the x direction. Now this guy has momentum in the x and y direction. Okay, since the final momentum must equal the initial momentum, these y component of the momentum must cancel. Okay, so here's the initial x component of the momentum equal to final x component of the momentum. Initial y component of the momentum equal to final y component of the momentum. And if in addition collision is elastic, then this must be true as well. Initial kinetic energy is equal to final kinetic energy. Okay, it turns out that if the two masses are equal, then after they collide, they will always go at a certain angle. Do you guys know what angle that is? You guys know it intuitively because you played pool, and subconsciously you've aimed you with that knowledge.
180 degrees.
It's not 100, 90 degrees. Okay, so if the two balls have equal masses, and if the collision is elastic, after they collide, they go up at 90 degrees. And you knew that because you've played pool and you made a shot. Okay. So let me tell you a way to make money in the pool hall. So what you need is, you need a cue ball that has a different mass. So while you're shooting, you use the cue ball that's regular, and when your opponent is shooting, then you switch the ball, and you can beat a world champion, you know. So all right. Do you guys need a break? I have 15 more slides, or maybe we can keep going. I know some of you are tired, but anyway. All right. So when I toss this object, what is the trajectory of this keychain? A parabola. Okay. When is it a parabola? I'm sorry? When only gravity is the force that's acting on it. When there is drag forces are negligible and stuff like that. All right. So for a point object going in a projectile motion, the trajectory is a parabola. So when you toss an extended object like this, see, none of these points are going on a parabolic trajectory. This point is not going on a parabolic trajectory. Okay, the tip is going on that trajectory. There's only one point in this object that's going on a parabolic trajectory, and that's the center of mass. Okay, so let's say you do a backflip. Only one point in your body is going on a parabolic trajectory, and that's the center of mass. That's your center of mass. Yeah. So when an extended object is tossed in a constant gravitational field, the center of mass travels in a parabolic trajectory. So for an object like this, you can find a center of mass like so. You just suspend this object. The center of mass is somewhere along that line. You suspend it from another point, and it's somewhere along that line. So the intersection of those two lines gives you the center of mass. So of course, if it's a three-dimensional object, then you suspend it from three different points. Okay, so here's the center of mass of this object. There's the center of mass of that object. Okay. So you see, the center of mass doesn't need to be within the so it can be an external point. Okay. So let's go to that. Okay, so if no external force acts on the system, then you'll see that the center of mass moves with a constant velocity. Okay? So external forces will accelerate the center of mass. Okay, so there's the center of mass. Here's how you calculate the center of mass of the system. You take, so this has x, y, z coordinates. The x coordinate of the center of mass is given by, you take the x coordinate of each particle, multiply it by that, and divide by the total mass. The y coordinate of the center of mass is mi, yi divided by total mass, and so on. Okay? Similarly, z coordinate. Okay, so for a continuous object, you just turn them into integrals. So the x coordinate of the center of mass is, you break it up into little pieces. dm is that mass. That's the x coordinate of that mass, and then you do the integral and divide by the total mass. Again, you don't have to worry about this. So anyway, here's the expression. Okay? And if the density is uniform, then the density cancels, and it can be written in terms of a volume integral. Okay, this kind of understanding is useful. Okay, so back in the old days, this is how they would do a high jump. Okay, so what's going on here? The center of mass of this guy is somewhere there. See, it's going over the bar. Okay, so let's say here's the bar, here's this guy, and in the old days, they would jump like that. Okay, I'm showing you sideways. There's the center of mass of this guy. Okay, and the center of mass went over the bar. Now, most athletes are, sort of roughly equally strong. And what you can really do is, when you're learning high jump and whatnot, the technique you're learning is how to get your center of mass as high as possible. And like I said, most people are equally strong, and you can get it up that high. This guy, he knew physics. Here's what he did. See, he's bent his body like that. when he was going over the bar. There's the center of mass. Now, he's not any stronger than anybody else. He can make his center of mass go to the same height, but now he can jump over this bar. He can beat the pants off of this guy. And that's what he did in the 1968 Olympics. Yeah. He was the first guy to do that. Yeah. And he won the gold medal, and now everybody does that. Okay, so in every jumping event, your center of mass is going below the bar. And who wins the competition? The guy who can get the center of mass as low as possible. You gotta have the perfect jump. Okay? So there was a hurdler, 440 meter hurdler, and he had a master's in physics, and nobody beat him for 10 years. I forget his name, but anyway. So he optimized his the number of steps between hurdles. Okay. All right, we've been talking about single particles, but all that we've said applies to systems of particles. So if you have a bunch of particles, there's the momentum of this guy. The momentum of the system is just the sum of the momenta. These are vectors, and you can add the vectors. So there's the momentum of the system. The net force acting on the system is time rate of change of the momentum of the system. Okay. So you can apply this formula, which is Newton's second law, to a single particle, or you can apply it to a system of particles. And if the mass is not changing in the system, then the net force is equal to mass times the acceleration of the center of mass. So you saw that in that simulation. Okay. There was no external force acting on the system, and so the center of mass acceleration was 0. Okay. So for this case, here's a torpedo or whatever, a missile that was shot. The force of gravity acts on it, and so that goes on a parabolic trajectory. And even after it breaks up into a million pieces, the center of mass is going on that same parabolic trajectory. Were you guys aware of this? You were? Have you? So I'll tell you how. You guys have watched fireworks? Of course you have watched fireworks. Have you kept track in the dark? You'll see that empty shell. You're able to keep track of the empty shell. And that's because you knew physics and you intuitively knew to look at the parabolic trajectory. So next time you look at a firework, see for the empty shell. Yeah, that's where the most of the mass is. And you'll be able to track it. Okay. Even in the dark. All right, now we'll talk about rocket propulsion. This is a conservation of linear momentum thing. So, all right, so here's you guys have shot a gun or not. You shoot a gun and you recoil. What was the momentum before you shot the gun? The total momentum of your system? 0. So if you're wearing skates on a frictionless surface, you shoot the gun, you shoot a bullet, you recoil. Your momentum plus the momentum of the bullet is 0. All right, you want to go faster, what is it that you do? Shoot another bullet. You go faster. You want to go still faster, what is it you want to do? Shoot another bullet. The momentum of all the bullets in you is what? 0. So, let's say you go in deep space. Start off with 0 momentum. Okay. You fire some exhaust and you'll go faster. And then you fire some more exhaust, you'll go faster, and so on. The momentum of the entire thing is 0 if you started off at rest. Okay, that's a rocket. So the operation of a rocket depends upon the law of conservation of momentum. All the forces are internal forces. There's no external force acting on the system, and so the momentum of the system is 0. Okay, so I'll give you a couple of formulae, important formulae, and then we'll get done. Okay, so let's imagine you're in deep space. Here's the rocket, and right now its mass is that, and it's going at this velocity. You want to speed up. What is it that you need to do to speed up? You need to fire a bullet. Okay, you need to shoot some exhaust gases. Okay, and you guys understand, if you shoot the exhaust gases faster, your recoil will be, you'll increase in velocity will be faster. All right, how do you shoot an exhaust gas faster? That depends on what fuel you choose. It depends on what it is that you're burning. Okay, so that's what you decide on the fuel. Okay. All right, so you shoot some exhaust gases and you speed up. What is the total momentum of this guy? That's equal to this momentum. Okay, well, what speed is this guy going at? So if the exhaust velocity was, VE, it's like this. Okay, so let's say I'm going on the highway at 100 miles an hour. I throw an apple in the backward direction at 15 miles an hour. What is the velocity of the apple for somebody watching from the ground? So I'm going at 100 miles per hour, and then I throw an apple like that. What does this guy see for the velocity of the apple? That's right. So 85 miles per hour. Okay. So this guy is seeing it as 85 miles per hour. Okay. All right. So the momentum of this guy is, see, now his mass is reduced, his speed has increased. This is the amount of gases he threw, and that was the initial velocity minus the exhaust velocity. Okay, so that's the momentum of this plus this. That's that, and that's equal to the momentum of this guy, which is that. Okay, so if you do the math, you rearrange all of this. See, this is the reduced mass. That's the change in velocity, dV, minus the exhaust velocity divided by dm. Okay, this is in free space. So you divide this by, so dV equal to minus VE dm by m. And then you do an integral. So this would be initial to final. Okay. So this is V initial to final point and minus VE log m initial to final. Okay. So anyway, if you do all of that, here's the expression you get. What this expression tells you is the final velocity of the rocket minus the initial velocity of the rocket is the exhaust velocity log m initial. What does m initial mean? The initial mass of the rocket, and here's the final mass of the rocket. Okay, why are they different? Yeah, a rocket is mostly fuel. A rocket is really a controlled explosion. Okay, so you see, the faster you want your final velocity, the greater you want this to be. You want the exhaust velocity to be greater as well. Okay, so the more fuel you burn and the greater the exhaust velocity, the greater your final velocity. Okay, so this gives you your final velocity as a function of how much fuel you burnt and your exhaust velocity. Again, this is in free space. Of course, we have to launch the rocket from ground level. Okay, so when you you have to account for the force of gravity, and this goes through all the derivations. So here's the change in velocity. Again, the same expression as before. And this guy is reduced by this amount because of gravity. There's the acceleration due to gravity and the time of burn time. Okay. So you can get the previous expression where in space where g is 0. Okay. And you'll get the previous expression. What does this expression tell you? This is mass times dv by dt. What is that? That's the acceleration of the rocket. And that is equal to the exhaust velocity again, times what is this guy? dm by dt. The rate of change of mass of the rocket. How's the mass of the rocket changing?
It's decreasing.
I'm sorry?
It's decreasing.
Yeah, it is decreasing. That's why you have the absolute sign. So that's the burn rate, at what rate you're burning the fuel. You want greater thrust, you want greater exhaust velocity and greater burn rate. Okay, so remember that formula. Greater thrust, you want, so this you choose ahead of time. Once when you're designing rockets, whatever fuel you choose, that's what determines that. The burn rate, and then you know how many engines you have. Oh, what does Elon call his big rocket? Starship. He wanted to increase the burn rate. He has 31 Raptors, or is it 33 Raptors? 33 Raptors. All right, so we'll quickly give you numbers on the rocket. Okay, so this was the space shuttle, and it took 8 minutes to get to orbit. Okay. These were the solid rocket boosters. When it was on the launch pad, it's heavy, so you need extra boost, and so you had these solid rocket boosters, and that burned for 2 minutes. And then, you know, they were jettisoned. And then there was fuel in this guy, and the fuel in that guy was, do you guys know what the fuel was? Hydrogen. Liquid hydrogen was the fuel. And when you burn a fuel, what is it that you need? Oxygen. You're high up, there's no oxygen, so you have to carry your own oxygen. So this thing contained liquid oxygen and liquid hydrogen. Okay. All right, so here's the tank. So you see, this is the liquid oxygen part, and there's the liquid hydrogen tank. So that was the fuel. Okay, I'll just give you a couple of numbers. Okay. All right, so here's the shuttle sitting on the launch pad. The thrust at liftoff. So this is generally the numbers for most rockets. So how much thrust do you need? The thrust should be greater than the weight of the rocket, otherwise you're not lifting off. Okay, and the thrust is, okay, so this is in pounds, 3.55 million kgs at thrust, and it weighed 2 million kgs. So if you divide thrust by the weight, what you get is 1.8, and that's generally the standard for most rockets. Okay, so the thrust at liftoff is about 1.7 to 1.8 of your weight. Yeah. So in the shuttle, these were the main engines. These are the solid rocket boosters. The main engines burned liquid hydrogen. Okay, and the main engine exhaust velocity was 10,000 kilometers per hour. It was burning 1,200 kgs of fuel per second. Remember, the thrust is exhaust velocity times dm by dt. So this number is 1,200 kgs per second. 1,200 kgs is almost eight small cars a second. It's burning 8 small cars a second. and the exhaust velocities were 10,000 kilometers a second. Okay. The solid motor rockets burnt 5,000 kgs per second for 2 minutes. Okay. Here's an amazing number. You guys know the horsepower of your car? You don't know the horsepower of your car? And you paid all that money for it?
Technically, it's my parents' car.
Yeah. So, I have a car that's 200 horsepower. Okay, 200 horsepower. What does that mean? My car is being pulled by 200 horses. Okay. This is 40 million horsepower. Okay, and that's the same as 20 Hoover dams. That little machine has the same power as 20 Hoover dams. Okay. All right, so look at this, and there's the space shuttle. Okay, this is 32,000 kilonewtons was the thrust. The Starship is more than twice that. This is a rocket. All right, guys.